Okay, so welcome back everyone to Comp 330. So as you probably immediately noticed, this isn't the normal lecture recording setting you're probably used to. For one, I'm in my home office, so this black thing you see here, that's my Blackboard. And so the reason why it's a different lecture recording setting than you're used to is because I gave the lecture this morning and I wasn't really satisfied with my explanations that I gave the people in person. And so I'm re-recording it. So hopefully at least the people that watch the recording will be satisfied with the explanations. Okay. Um, Before I do that, before I jump into the material of today's lecture, which will be about undecidable problems about context-free languages, so exactly the same material covered this morning, I just want to make a quick clarification note, which I had also made this morning during the actual lecture, is that I've added a video. So I added a video about lecture 23. And it's really a clarification about the notation in lecture 23. So in lecture 23, I was talking about properties of CE languages. And so the way I was denoting that was the property of L of M. Okay, so this is a property of a CE language because L is accepted, L of M is a language accepted by a Turing machine. But there was a bit of confusion, I think, in this notation because I was saying that a property of a C language should be implementation independent. But of course, if you just have a property that's given a language, it doesn't matter. The property actually doesn't care about what the, say, implementation of the Turing machine for the language is. And so really what I should have been doing, I should have been explicitly announcing that this notation was referring to the fact that, yes, I did have a language which was CE, but I had a language which was CE, which was then accompanied by a Turing machine, which accepted that language. So really this M here is an extra parameter to the property P. So you can think of P being additionally parameterized by M. And the reason why we need this parameter n, the reason why we need to talk about this parameter n, is because if I tell you, given some CE language L, is L equal to sigma star? Well, you actually need a way to represent L. And in this class, so far, the only way we've seen to actually represent CE languages is through Turing machines. So if you want to be able to create an algorithm that deals with CE languages, what you need to start with something that can, in a finite number of letters, let's say, because a Turing machine can be represented as a finite string, actually talk about the CE language. And so the property P is really intaking, yes, a language, but it's also additionally parameterized by a Turing machine M, and M is the actual thing that's allowing you to know what L is. And so then a property of a CE language is when it doesn't matter what implementation of the same language L you give. If it's either M1 or M2, the answer to the property, the evaluation to the property is always the same. Okay, so there's this extra video in which I explain this. And you might be thinking this is probably unrelated to today's material because we're sort of moving on from the classical questions about CE languages, but it's actually quite relevant. So I'll show you why in a second. The topic for today, where I will tie this extra note back, is undecidable problems about context-free languages. Okay? And I can immediately actually refer back to this note, because if I say I have a undecidable or decidable decision problem about a context-free language, it means that I'm asking a question about a context-free language, sure. But to be able to actually talk about that context-free language concretely, I need some way of actually representing that language. And we saw that for context-free languages, there are two models to represent context-free languages. The first one is a context-free grammar, and the second one is a PDA. And so when I say I'm making a decision problem about a context-free language, I'm actually saying that I'm given some finite representation of the language. In this case, it's going to be a context-free grammar. and I'm going to ask a question about that language generated by that context-free grammar. Okay. And so when I say an undecidable or decidable problem about CFLs, I'm saying it's a decision problem about a CFL, but parameterized in all of our cases through a grammar. Okay, and so what are some decision problems about context-free languages? So recall the following two decision problems. Okay, which in fact we showed, I think during lecture 13 or 14 or something, were decidable. So the first one was the is in or the membership decision problem. But it's the membership decision problem for a context-free language, right? And so in this case, the is in decision problem is parameterized by a grammar G and a string W. And what the decision problem asks is, given a context-free grammar G and some string in sigma star, is W in L of G? So really, this is a decision problem about a context-free language because we're asking about the language generated by G, but we actually need G to talk about what the language is, right? Because, you can imagine you have your languages here, right? But languages typically are infinite, right? And so how do you actually, in a finite number of symbols, represent an infinite context-free language? Well, the only way to do that is through the computational models, which model those languages. Okay, so the first decision problem about CFLs and consequentially about context-free grammars was the is-in problem. And we saw that this problem was decidable. In fact, it was efficiently decidable through the CYK algorithm. And really, this should be the CYKS algorithm because the actual discoverer of the algorithm had as last name S for Sakai. So really, this should be the CYKS algorithm. Okay, but this is an efficiently decidable decision problem because the CYK algorithm, it can be shown, runs in cubic time. And then there's another decision problem about context-free languages, which is decidable. And we also saw that in class. It's the emptiness problem. So the empty CF decision problem, where, again, it's a question about a context-free language, but it's parameterized by a context-free grammar. So we have some context-free grammar, which parameterizes the context-free language. Okay. And in particular, which parameterizes really this decision problem. And it asks, or it says, given a context-free grammar G, is L of G equal to the empty set? Okay, and we saw that this was also decidable, so this is also decidable. And it's decidable through this gen algorithm, right? So if you remember quickly, the gen algorithm, what it does is it works bottom up. It says, what are the terminals which in one step derive only strings of terminals? And then it works up, right? So then it asks, what are the terminals which in two steps derive only strings and terminals, and so on. And if the start variable is in that list, which is called the gen list, then that means that the grammar generates at least one string of terminals, otherwise it doesn't, and that means that L of G is empty. Okay? Okay, awesome. So those were the decidable problems about context-free languages. Now, there turns out to be many undecidable problems about context-free languages. So there are many simple decision problems about context-free languages. So to name just a few, which we'll study in this lecture, there's the all CF problem. So in the all CF problem, we're asking a question about a context-free language, but this is given through some context-free grammar G. And what the all CF problem asks is, given a context-free grammar G, is L of G equal to sigma star. Okay, so in other words, in the set of terminals of the grammar G, is L of G equal to the set of all strings that are defined over that set of terminals. So in this case, sigma refers to the set of terminals of G. Because remember, G is a four tuple. I'll probably get some of the order backwards, but a set of variables, a start variable, a set of terminals, and a set of production rules. Right? And so what the all CF problem is asking is, given this context-free grammar, given this four tuple, does L of G generate every possible string of terminals defined over this set of terminals? Okay, so that's the all CF problem. And it turns out that the all CF problem is undecidable. We will prove this in a second. There's also another very simple decision problem about context-free languages known as the intersect problem. So the intersect CF problem is parameterized by two context-free grammars. And it asks, given a pair of context-free grammars G1 and G2, is the language generated by G1 intersect the language generated by G2 not equal to the empty set? So it's asking, are there any strings in common between L of G1 and L of G2? If yes, then the solver to intersect CF should output yes. If no, then it should output no. Yeah. And so because we have the time in this case, because I have infinite time in video recordings, we'll actually be able to show that this is undecidable as well, something that we didn't get to do during the lecture. So this is also undecidable. Okay. And what we're going to do first, though, is we're going to start with the all CF problem. And we're going to show that the all CF problem is undecidable. So I'll end the video on that. I'll say that we will show that the all CF problem is undecidable. And to do that, we'll, of course, need a mapping reduction. And in this case, the mapping reduction is going to be from the not halting problem to the all CF problem. Okay, and I'll do that. I'll do at least the start of that in the next video.